and within those subframes, there are 20 time slots. This is used to break down your download synchronization signal and then your upload, and there are different modes you can choose from depending on how much weight you want to put into upload throughput and how much weight you want to put to download throughput. So Baicells supports two main configurations. That's configuration 1 and configuration 2. Configuration 1 has equal weighting between uplink and downlink, and there are 5 millisecond spacing apart between switching from downlink uplink, so it has better latency. Then the other configuration, there's up to 6 configuration total, but these are the two main ones standardized that we support based on our customer needs. The other configuration 2 has a download upload ratio of 3:1, but it doesn't quite equate to raw throughput that way. There are some overheads that are taken into. Within the frame, there are special subframes. These are used for overhead information, the synchronization signal. Those are all stored in here. And those are stored on subframe 1 and 6. You can see D is for data throughput download. S is for the special subframe where you contain signal information, broadcast information, sync information, and whatnot. U is for uplink. The thing to keep in mind is that to switch from uplink to downlink, you would need to put in a special subframe. From downlink to uplink, you would need a special subframe to make it work. There are other configurations where you only would see one special subframe. Those tend to be, they would go from uplink first, and then they would use a special subframe to switch to downlink, or vice versa. Oops. Modulation and coding scheme are the primary determinant of your throughput speed. This chart is very useful as a rule of thumb on what you should expect from every throughput. All our CPEs have an MCS rating on them. It would display in, I think, in the overview menu. And that's displayed in these cryptic numbers of 0 to 28. And this chart breaks down to what you should be able to expect those throughput ratings. In TDD, we assume 20 megahertz bandwidth for both these charts. Our Cat4, it does 1 transmit and 2 receive antennas. If you have a MCS value of 22, that means that you were on 64 QAM, and you should be expecting about 51.7 in terms of downlink. And then uplink MCS, it says 22 ratings, you should be expecting about 18. Here's another example of peak data rate. Assuming we're using subframe assignment 1 and special subframe 7, we should be expecting these uplink and downlink values based on 20 megahertz bandwidth. In our HaloBs, we support 2 special subframe formats, configuration 7 and configuration 5. These are a little, just a shortcut, a rule of thumb for you to understand them. Configuration 7 covers about 18 kilometers of cell range, and you would only use configuration 5 if you absolutely need to cover additional area or widen your cell range. It does increase your time delay, so we normally just recommend sticking to the default configuration 7. That's good for most network or most deployment. two carrier HaloB, split sector, and carrier aggregation. The special thing about Baicells is that we have HaloBs that can support split sector deployment using one device. It would add up to quite a bit of savings. We call that dual carrier mode. Carrier aggregation is adding, combining two channels, let's say 20 megahertz apiece, for double the throughput. For either mode, we recommend every carrier using a single full-port antenna or a two-port antennas, preferably cross-polarized. We do have the equivalent of spatial separation using cross-polarization. Does anyone have any questions about carrier aggregation or dual carrier mode? And yes, I think, go ahead.
Sorry, Ian. We did get a question. We do mention Cat4. Do we support higher carrier aggregation categories?
We have Cat6, and we're currently testing Cat15 UEs in our office right now. And Max, can you confirm if we'll be sharing these slides afterwards? This is the basic terminology for LTE network. PLN is public land mobile network. This is a special ID that's applied to every network licensee that identifies if you're a Verizon or AT&T or whichever network you have in your region. The tracking area code is a further refinement of that. You can assign specific tags to maybe different area code or just different clusters of towers. Your ECI is what identifies the individual physical location it's on, your tower itself. Your PCI would further refine that and would show your sector, which sector it's on. For PCI planning, we recommend that every sector has its own unique PCI, and I'll go over the detail a bit later on, but that's just the base rule of thumb. The simplest solution would be doing an increment of 4. That means if you have your first sector assigned, let's say, PCI of 1, your next sector could be PCI of 5, and so forth. That would avoid some PCI collision. The primary reason we assigned this method is actually PCI is derived from a formula based on your primary synchronization signal times 3x your secondary synchronization signal. PFS is actually what you're looking for because you have a value of 0, 1, and 2. So you would have to rotate that between a site. You don't want the same PSS on adjacent sectors because the overlap will have synchronization signal clashes, and then we would have drop packets and data. Once the CPE knows the HaloB's PCI, it can locate the reference signal, and the reference signals are known to both the transmitter and receiver, and it will use this information to start the attach process. For downlink, the reference signal helps the CPE estimate channel conditions. It can also use it to calculate your interference levels as well. We'll go over that a bit later. Uplink, the RS estimate channel quality, different and allocate resources to CPE. HaloBs in the same site and area should not have the same frequency or PCI. So let's talk about partially about frequency planning as well. For normal fixed wireless, we like to use a AB configuration where, let's say you have 2 frequency max to use. You would do frequency 1 on sector 1, frequency 2 on sector 2, frequency 1 on sector 3, and then frequency 2 on sector 4, and so forth. This would help mitigate interference. Doing a lot of optimization, I see that people are having interference issues, and most likely the first thing I look at is how they do their frequency rotation to see if there's any overlap between adjacent cells. If I see any of that, that's a sure sign you're going to have problems. Here's the basic formulation of how to derive a PCI. There are different methodology as shown in the a different online calculator. The most basic one I like to use is the PSS plus 3x the SSS. It's really simple. Just keep in mind that there at a certain radius you can start reusing your PCI, but if you can help it, just keep all your assign each cell a unique PCI. And so as I stated earlier, PSS ranges, there are only 3 values, 0, 1, and 2. I think this is based on the default deployment of 3 sectors when that standard was first formed. And if you need a link to this PCI calculator, I can send it to you, or I can give you the Excel formula. It's really easy. The equipment identifier, if you look on your phone, you'll notice when you activate your phone, they'll ask you for IMEI quite a bit. That's your physical equipment identity. Your IMSI, or we call MZ, is your SIM card identity. And this is how it's breaking up. 3 digits are assigned to the MCC, which is the country code. Up to 3 digits is your operator code or your PMLN, and then the last digits are your actual subscriber identifier. Block error rate. This is very crucial for throughput. The higher the block error rate, the worse it is, the more drops you have. So as a rule of thumb, I look for, if anything more than single digits, that's a sign of some potential interference or issues. These are the different metrics we use for LTE. The main one you should concentrate on are RSRP, reference signal receive power. This is the average power of LTE reference signal over the entire band. So this does change depending on if you have a 5 megahertz channel versus a 20 megahertz channel. Those your RSRP will change accordingly. RSRP is your reference signal quality, receive quality. And the considered good range are -3 dB, and then the bad range is worse, 19.5 or worse. And this is the formula for it. You can take a quick snapshot of it, but I think we'll be sharing the slides afterwards.
Hey, and we did get 2 questions I missed.
Yes, go ahead.
What happened if we use the PSS equals 0?
For all of them?
That is the extent of the question. What happens if we use the PSS equals 0?
No, we can use, we had to do a rotation of PSS 0, PSS 1, and PSS 2. Those need to rotate. Any adjacent cell cannot have the same PSS number, and then any opposing cell cannot have the same PSS number. that will cause what's called a PSS clash. It's like if you and I were yelling at the exact same time, no one would understand the both of us. But if I tell you to yell at time of 11 o'clock, let's say PSS 0, and then I will follow up yelling at 12 o'clock, we won't have that problem. We're trying to say, hey, this is my information, call me. But if we both say the information at the same time, no one would understand. So it's very important to rotate them, and then but rule of thumb, any adjacent cell should have a different PSS. You can use the same PSS if the sectors are back to back, let's say 180 degrees from each other. That's counting on good antenna front to back ratio. We'll talk about that in a bit later too. The next very important metrics is SNIR and CNIR. Your throughput, we brought up MCS earlier. That's a direct translation of how the network is interpreting your RSRP and your SNIR to come up with that MCS rating. I can almost tell you what the throughput might look like based on SNIR and the RSRP of looking at alone. Rule of thumb, the bigger the number, the better your service quality is. I would point out for a good throughput, a healthy network, look for a CNIR of in the teens. If you see anywhere in single digit, that may point to some issues. I would look into those areas. And in the negatives, that's really bad. So this slide shows you the difference between SNIR and CNIR. Just the main takeaway from this lengthy slide is that they are both a measure of signal quality. You want your voice to be louder than the voices in the crowd if you want your clients to be able to hear you. That's what it boils down to. The next point I want to make sure you take away is that you see two different CNIR reporting. We have CNIR statistics for every single receive antenna. So depending on which CAT CPE you have, you can see up to 4 of these. Look out for them. They should be within 3, maybe up to about, I say 3 dB in terms of plus or minus 3 dB apart from each other. But any more than that, it could point to potential issues, whether is it with the antenna or something's up with the network, because even with multipathing, you shouldn't be fluctuating that much. So that's another good troubleshooting method. The difference between RSSI and RSRP. Both of these are measured only in symbols containing reference signal. RSRI can measure the entire block of your channel, and RSRP measure the power of the specific resource element. Now, just as I mentioned earlier, these are what we would consider good signal, but technically from a operator standpoint, I generally shoot for if it's better than minus 85 dBm, and like I said, SNIR or CNIR in the teens, you should expect decent performance out of them. Next, we'll go over some how to read the antenna spec sheet. This is very important for network deployment. Just basic understanding of what values to look for and how to read the antenna data sheet. This is a typical data sheet I took off one of our vendors. I'll go over each one of these terminology and then which one you should pay attention to. So polarization. On the diagram on the right, it shows you kind of a visual of what polarization means. There are vertical polarization and horizontal polarization. There are, they call them cross-polarized. Usually show up as like 45 degrees. I prefer cross-pole antennas because from a theoretical standpoint, they have the same MIMO performance as spacing your antenna at 2 to 7 frequency lengths apart. When you see antenna gain, this is what it means. It's just in reference to a theoretical antenna of perfect, imagine a ball. If you squeeze that ball down, the ends of the ball will expand out. The difference between the original ball shape and that compressed, expanded shape is your antenna gain. So on the right, I have a antenna pattern that's in a lot of data sheet. So if you see the side lobe, that's usually a remnant of the original isotropic antenna or the perfect ball slash donut. The difference between that and your main lobe right here, you can see the big bulb over here, is about 19.5 dB, and that's how they list it as antenna gain. And this goes through the flattening analogy I went through earlier. Beam squint. A lot of manufacturers won't have this stats, but all that means is how accurate the beam is in comparison to where the antenna is pointed. It may be off by a few degrees. So if you see beam squint of 3 degrees, it means if you look directly from the back of the antenna out to where it should be facing, it may be off 3 degrees to the left or 3 degrees to the right. Half power beam width. All that means is that from the maximum received power you get at the main lobe, go down 3 dB, and that's how to determine your antenna beam width. So if you see this dotted line right here on the middle diagram, that's 3 dB down from the absolute best power. And where that intersects with the main lobe, that determines your antenna beam width rating. Impedance. Most of telecom equipment are rated for 50 ohms. All you need to know is all of your cables, antennas, active equipment, make sure they're in the same impedance. If you don't, you're going to have some visual problem. And that just means, let's say I use a 1 meter pipe, and then the next pipe is only half a meter. The wire is going to be forced against that half meter. Some of that's going to reflect back. Well, water is not a good analogy, but let's say light, for example, right? It's like if I'm shooting a light of a meter wide through a reflected mirror hole that has a hole of half a meter, half of that light's going to reflect it back. That's what visibor means. It's reflected power if there are any impedance changes. I'm listing right here like different impedance for different technology / industry. Just as a reference, like I said, most of the time, everything you have in wireless should be 50 ohms. This chart is a pretty great summary of how to understand return loss. This is a really good reference. I have this saved on my OneNote. So if you have zero return loss, that means 100% of your power from the email B gets passed through the antenna and out into the world. And then it scales accordingly. At 10 dB, only 10% of the power. I'm sorry, I got that backwards. At 0 dB, 100% reflected, that means you get nothing to the antenna. And this is logarithmic scale. If you notice, an increment of every 3 is a doubling or half of that power, and an increment of 10 is every 10 or 10th of that power. That's a really good rule of thumb to remember in terms of TDB. I'll go over that in a minute as well. Another line item you see a lot is mechanical and electro down tilt. This will help you have a pretty good idea of what each one of these does. Mechanical down tilt just means you physically are tilting that antenna. For electrical down tilting, it's in an antenna, there are multiple antenna elements, and if you apply different power to each one of those elements, it will shape the antenna pattern accordingly. It's like having 2 opposing waves. If you have them at equal strength, they will go straight out into the world. If you have one element with slightly less power, that lobe will more likely will bend up or down depending on that element is, depending on where the weaker power is, and that's how electrical down tilt work. This diagram is a great visual of what to expect. When you electrical down tilting, it's pretty easy to imagine. I think anybody can imagine. It's just tilting that beam directly. For electrical down tilting, you're actually bending that beam. The next plot, the next picture will be pretty interesting. So this shows you what mechanical down tilting does to a physical coverage footprint. This is theoretical based, but as you can see, electrical down tilting reduces the footprint, but it also squishes the side lobe out more. With electrical down tilt, you reduce the footprint evenly and maintain the same pattern throughout. So this is more useful in controlling side lobe bleed off, and it's a bit more precise in kind of narrowing down exactly what you want to cover. This is a free tilt calculator online. I use it quite a bit. Just enter the antenna height and then what's your vertical beam width. It does a quick Pythagorean theorem calculation, and you can get to see how far away the main lobe is. It breaks down like the top 3 dB and the bottom 3 dB of that main lobe and where it's going to reach, and that will give you an estimate on how far you should expect to cover based on your down tilt. Without RF propagation, this is a good kind of planning aid in terms of figuring out what down tilt you need to apply to your sector. In RF, you'll see these a lot, dB, dBm, and dBc. dBc is a bit rarer because that's mainly applied for when you do PIM testing. dB is the ratio power, it's logarithmic scale. Remember I mentioned before, every 3 dB is an increase, it's a 2-fold increase in power. Every 10 dB is a 10-fold increase in power. Basic rule of thumb. That directly converts into dBm, which is the relative signal strength that's compared to a milliwatt. So here are something to memorize as well. Just remember 1 watt equals to 30 dBm. Remember up here when it says 10 dB is 10 times that power. If you add 10 dB to 30, that's 40 dBm. That's 10 times the power, 1 watt versus 10 watt. And then 3 is 20. 43 dBm is 20 watts. dBc is the signal strength relative to known strength. So in, let's say, a PIM tester, you would assign it I usually test at 43 dBm for most cables and then at specific bands. And here's the link to a very useful little site, just in case you don't want to use the rule of thumb I showed you. This will give you an exact number as well. Free space path loss. This is a very good, I use this just to estimate Excel calculations in terms of how far you would expect to see the signal. And you can use this as a reference in terms of checking your power output. But as a reference, here's the formula for calculating these in miles and feet. If you need, I can give you the formula to calculate it in meters and kilometers, but they're pretty similar. So at a mile out, you should be expecting 107 dB down from whatever signal. Let's say your antenna is broadcasting at, for simplicity's sake, plus 37 dBm. You should be expecting to be down 107 dB at a mile out from that. So that means you should be seeing a signal of mix 70 at a mile out. These are good visual aids in understanding how RF propagation works. It is a combination of, if you could visualize a combination of like water ripples and how light bends. If you plot a sight down the middle, looking at a top-down view, 2D, it acts similarly to how a wave ripple. This light source I'm showing, it's another property of RF prediction where it does bend around, refract and reflect around the object a little bit. And this also shows you like penetration. So if you imagine this marble to be a house per se, right? This bright spot may be the window of that area because there are different loss properties for thickness of material, what type of materials. Refraction is just a change in direction of a wave passing from one medium to the other. This diagram off to the right is a pretty good example of that. Reflection is just how things are bouncing off surfaces. And then I mentioned different material and insertion loss. These are some typical values for tree loss. If your tower is going through a trees, you can expect about 12 dB down from if you're running at 2.4 gigahertz, let's say. This is just another example of how to imagine radio propagation. As you can see, the lighter area will be stronger signal and the darker area will be worse signal. As you can see, the density of blocks kind of imitates loss in a way. I mentioned earlier, this is an example of what our prediction looks like. This program we use to predict this is HaloB. This is just based on terrain data, antenna output and height, and they will give you a rough idea of what to expect and the coverage footprint. Now that we've finished section 1, is there any questions? I know I may have gone a bit fast.
Yeah, there was one question that we missed. If I have set If I have to set reuse to 1 and all 3 sectors at the same frequency, does the eNode B help with frequency allocation for CPEs to minimize interference? And this is for the R9, the Nova R9.
One more time, please.
Okay,
Reuse of 1, 3 sectors.
Yeah, so set reuse to 1, all 3 sectors at the same frequency. Does the eNode B help with frequency allocation for CPEs to minimize interference?
Unfortunately, no, all of our products, each cell is its own eNode B, and there are, it can be done depending on the core and your scheduler you use. So if you have your own core that supports different scheduling methodology, the one that we use most is round robin, and that's just typically in and out. That doesn't take any of that into consideration. For if you have for a normal like mobility deployment, you would have the BBU controlling 3 sectors of cells. And that BBU, because it's on the same platform, it can do some mitigation in that way. But the long and short answer is no, because each one of the cells is its own eNode B, and they don't quite communicate with each other unless you have a core that supports a bunch of those functionality. Mm. I hope that answers your question.
Yeah, and this is Jesse here, so I'll try to comment on that as well. So I think you touched, Yan, on the fact is that most of our product line is currently kind of the small cell portfolio. So the baseband and radio unit, they're combined. So there's no shared BBU, right? If you're going to do 3-sector deployment, it means deploying, potentially three Bs in our case. So yeah, without that central brain, there's not, they can't really take too much advantage using like ICIC type reuse 1 techniques. So yeah, in that case, no. Now we do have, it is a feature, it's not heavily used, but we do have some basic form of ICIC where you would kind of just statically set what percentages, which portions of the resource blocks were to be used. So you could statically set it, so maybe each one gets 33% of the resources for the channel that's being shared across. And then, of course, LT is already natively designed to support single frequency. That's the kind of the purpose for the PCI, to have the reference signal on different parts of the frequency. So it would work, even without any kind of reuse 1 technique, it still works. It's just obviously there's going to be, some interference, especially in the overlapped areas.
Correct, and with the assignment that Jesse brought up, you are reducing your resources by 1/3. Like I mentioned, so the single frequency reuse, where you're using a same channel on every cell for the entire network and distinguish it based on PCI and RSI, that will work, but you would need a scheduler to offload your traffic very quickly. So I think a lot of the carriers here are using PCI-based scheduler, where they just serve the customer with the best signal quality first, and then that means the user at the cell edge gets reduced throughput and worse latency. Again, a lot of that functionality is tied to the core. Okay, Jesse, we're up at section 2.
Yeah.
My apologies.
Okay.
There was another question that came in right then. Can you set more than 30% for each cell? This will end up with an overlap on RB, but we can statically assign our beads for overlap only at congestion hours, we can create more capacity in a noisy environment.
Yes, I believe so. So again, this reuse one, the feature set's not commonly used, so I'd have to confirm the function, you know, I would think in theory, because it's pretty static set, right? You can just set it to whichever, you know, PRB blocks you want to use, you know, effectively picking which portion of the channel. So yeah, you could do that and have some overlap and maybe reduce a little bit of performance in the edges there. So yeah, I would certainly think it's doable. You know, obviously so I'll be covering the products in this next section, but you know, eventually we're working on releasing the more traditional distributed base station. So there will be a central baseband that will be 5G ready, and that would allow, right, for more kind of reuse one techniques. Yeah, for the time being, with our current kind of small cell form factors, you know, there's a limitation there when it comes to reuse one.
Okay.
Okay, so let me go ahead and share my screen here. Here. So I'm not sure if this is going to work this way.
Right now we see the notes section.
Yeah, okay.
I'm
not sure how to...
For that 5 again, there should be a thing at the top bar that'll tell you to switch.
Oh, is there? Let me give that a try. Display setting.
And then, yeah, right there.
Swap.
Switch.
There we go. You're good?
Yep.
Okay.
Actually, now we're seeing everything.
Yep.
Now we're seeing both if there's underside and the regular slides.
That's the only share one monitor. I think you're sharing all your monitors.
Yeah, I don't know. It seems maybe WebEx is not as capable with dual screens. So I'll just share it like this. I think it's okay. Let me close this.
That'll work.
Up. Yeah. Okay. So this section, we'll just do kind of a quick review of some of the mainstream products we have. We're not going to be able to cover everything. You know, we do have quite the extensive product list. You know, and one thing I think, you know, we have kind of advantages. You know, we work with a number of integrators, and we pretty much cover most bands. And we have different products, you know, across the spectrum, you know, from very small cells at 50 milliwatts all the way up to 40-watt base stations. So we kind of cover a range there, and you know, we can do kind of custom builds depending on projects too, really depending on customer requirements. But we do have our mainstream products. At least in the U.S. market, you know, we also have a number of off-the-shelf products. Obviously, whichever market you're in, you know, we should have some distributors and partners, you know, that may have certain inventory as well. But we'll try to cover the main products here. So here are our single carrier base stations. We have, starting with the 227, this is showing all the outdoor units. So the 227 is the only one here that has the integrated antenna. So this is also the only one that's PoE powered. So this is really designed for a small coverage footprint, but also designed to be very easy to deploy. So if there's certain pocket areas, micro-pop type scenarios, that's a really good, quick, and easy deployment. And then we have our 1 watt product and 10 watt products. Now which one you would select is really based on, the band and regulatory requirements. For example, for the 3.5 gigahertz in US, the RP is quite low, so the 1 watt base station is what is selected. But yeah, based on, your coverage footprint you're looking for and the, regulatory requirements, it really depends on, which of the products you would select. One of our products we introduced last year is what we call the 436Q. Currently, this is just available for the 3.5 gigahertz, so our band 48 for the CBRS market here. This could also be done in other bands, but for the moment, that's the only one we are currently using. But this is our dual carrier-based station, so it can be configured as either a carrier overlay or running in carrier aggregation mode. Okay, so yes, again, so the main difference compared with single carrier base stations is really just the extra 2 ports and the ability to run the DC for dual carrier or CA for carrier aggregation. One thing that we see that's popular with this deployment is if it's not a high density area, you're just looking for maximum kind of coverage at the lowest cost. Using 2 antennas, say 2 120-degree antennas back to back, can provide, we kind of call that the butterfly coverage. It's pretty nearly 360 coverage, and we see that as one, cost-effective option. If you don't need the CA capacity, you're just trying to get some coverage in rural areas. So we call that kind of the split mode configuration, or DC, and then of course we have the CA mode as well, which you could add a 4-port antenna to, to have the maximum aggregate throughput for the downlink. Okay, for the CPE side, we have ranges from the indoor to the outdoor. Here's one of our indoor models that we have a Cat4 and Cat6 unit currently. It does have the built-in Wi-Fi. It's really, designed just to be, one unit acting as the router and LTE for the backhaul. Okay, for the outdoor units, we have range from, we typically have about 2 models for each category. So Category 4 and Category 6 are the main products we have currently. As Yen mentioned, we have a Category 15 that's currently under trial. So we expect to add the Cat 15 to our product line here shortly. And one difference, kind of to point out, for the one difference with Cat 4 and Cat 6, so for those that aren't too familiar, first of all, with the categories. So Category 4 is in a previous 3GPP release. This is before carrier aggregation was added. So Category 4 is more of your a little bit more cost-effective unit, but it only supports single carrier. Now, our Cat 4 units have a 2x2 antenna, and one thing though is with our Cat 4 is it's a little bit higher gain. So we have Cat 4 CP up to 19 dBi, but it does only support the single carrier, and the uplink is limited to the 16 QAM. So when you go to Cat 6, The advantages with Cat6 is now you can take advantage of the carrier aggregation, and you also, with our Cat6, we do support the 64 QAM uplink. So you get a little bit better performance on the uplink as well. But the antenna gain, we do use a 4x4 antenna, so the gain is slightly reduced compared to the Cat4. But the primary differences between the categories is really about is carrier aggregation supported or not, and in our case, 64 QAM is supported with Cat6 as well. To the far right there, we do have kind of a novelty product that we built that we call our LTEU. So we're the only vendor that has developed an FDD solution for 5 gigahertz. And this was, really for kind of fixed wireless and certain use cases where the uplink was, very important. And so we do have our own LTU product line. It is a little bit custom in the fact that we're doing FDD with it. But depending on the use cases, it does perform quite well. Okay, as for the core options, again, our product line is, all 3GPP based, standard based. So we do have, quite the number of customers that work with any, core vendor. So, that is, again, the beauty with standard based solutions. We're not doing anything proprietary with our, with our gear, as it pertains to, the S1 messages and all that with the core, with the EPC. As for our product line, we have really the 3 main products. One is the Baicells Cloud Core. So with this, we have hosted, we use Microsoft Azure data centers, so we have our own Cloud Core hosted. And the one thing that we are doing a little bit different is with our Cloud Core, we kind of built it to try to make the deployments as easy as possible. So when you purchase a base station from us, it's already programmed for the cloud EPC. So if you were to just power it on, it would automatically connect and could become active without, any configuration made at all. So, that Cloud Core for us is really to try to streamline and make the installation as easy as possible, and to, remove that initial investment that traditionally was required when it came to deploying private LTE networks. So, probably the bulk of our U.S. customers are still on Cloud Core, but, we kind of look at it as it's a good entry into, getting onto deploying your LTE network. But we normally see people, when their network gets large enough, that's kind of like a migration path to where eventually they would go with a local EPC, depending on their requirements. But the one uniqueness with our Cloud Core is we're not taking the actual user data, so it's really just there for control plane. So with our Cloud Core, we have our own web interface where the customer can manage their equipment, but also manage their SIM cards. So they could import, activate the SIM cards, and from there be able to attach any kind of UE to the base station, which is connected to the Cloud Core. And but what is different with our HaloBs is when it's configured for the cloud EPC, it will enable a LIPA-like local breakout function, which we call LGW for local gateway. So the actual user plane, the user traffic will route through the local gateway of your network. The user traffic does not go to our core, right? So the latency, everything stays on, is reduced, and the traffic will stay on your network. So in that way, it should behave pretty similar to like a Wi-Fi AP. Okay, so then we have, I'll move to the HaloB. So HaloB is another option where it could still be used with the Cloud Core. The difference with HaloB is it's embedded EPC functions into the HaloB itself. So for us, HaloB is just kind of like a toggle switch. So it does require a license, but if you were to import the HaloB license to your base station, you could just flip the switch to enable HaloB, and that would start the soft core network solution, which basically embeds the MME and HSS function into the ENOB itself. So the user plane still does the local breakout, but the MME function would essentially move from the Cloud EPC to the ENOB itself, which is, really the most robust solution you could have. You don't have to worry about S1 disconnects or anything of that nature. So HaloB is actually our second most popular core solution. And for HaloB, it does come in a couple modes, and I think that's in a later slide we can go in more detail. And then local EPC, again, there's many EPC vendors out there. We do have our own as well. But yeah, if you get to a point where you require certain functionalities, whether it's handover with mobility, if you need better QoS handling, charging capabilities, all of this would require a local EPC. Our Cloud EPC functions, HaloB functions, they are quite limited as far as functionality goes. So yeah, once you get to a point, if you require further feature sets, you would have to go with the local EPC. Okay, this kind of reviews actually the US Cloud Core we have. So we have two EPC environments that are load balanced among each other, and then each operator would be connecting essentially to the same core. We do have two MMEs, so for redundancy and load balancing, every ENOB will be connecting, to both of those cores. And yeah, so essentially it is a shared core, but the user data itself, again, remains on the operator's network. Yeah, so this talks a little bit about the LGW function. So again, LGW is our local breakout feature. So we do have the three different modes here, with default being NAT. So by default, all of the UE traffic would just simply NAT to the IP address of the base station itself. You could switch to the router mode, where you define a certain subnet that would be used for assigning IP addresses to the UEs. And then bridge mode is our most commonly used, where every time the UE attaches, the ENOB would, on behalf of the UE, run a DHCP request to pull an IP from your own DHCP server, and then associate that with for the UE for that particular UE's traffic. I believe there's more detailed on another slide we can go through. Yep. Okay. So one kind of difference with LTE as well is in LTE there is no MAC address being passed, across the network on the LTE side. So it's not like the traditional, you can identify, certain hosts by their MAC address. When it comes to LTE, you identify by the IMSI. So what we did is we will convert the UE's IMSI number. We have a formula where we calculate that and convert it to a MAC address. So once we have the MAC address, we will set up a virtual kind of interface on the base station, which will use that MAC address. But ultimately, the actual traffic in NAT mode will be NATing through the ENOB itself. But the challenge with NAT mode is once things are NATed, you can't exactly access the device, behind something that's NATed, not without port forwarding. So one of the things when it comes, for fixed wireless purposes, the operator, still wants to be able to remotely access the CPE. So for NAT mode, what we did is we will take the last 4 digits of the IMSI, and in front of that, we'll add the number 5. So basically, whatever the last 4 digits of the IMSI is, with the 5 in front, that would be the port to access the CPE's web GUI. And that would forward to port 4, actually, I think this is misspelled, 443. For HTTPS, it would point to that port. So essentially, you can still access all of the CPEs, even with NAT mode. And we can kind of, when we get to the slides covering the configuration, we can kind of look at that, because when you log into the HaloB itself, it will print out a list of all your IMSIs or your UEs that are all attached to that particular HaloB. And there is a link you can click on that will bring you directly to the CPE's web interface. So point being, even with NAT mode, we can still remotely access the CPEs. So router mode, you would define certainly a subnet for what your LGW IPs are for that particular B. It does require, though, that you would have to add static routes. So because it's going to be on a different subnet, so you would have to add routes to be able to point to where that particular B's IP address is, so that it is a routable network. So there is that caveat, but yeah, if it is depending on the network configuration and design, that's really going to dictate which of the LGW modes would be used in that scenario. But this one's not as popular, but it is possible to just set a certain subnet for the LGW IP addresses. Okay, then in the bridge mode, this is where it would take that IMSI, convert it into a MAC address, and then use a DHCP request based on this MAC address. Now, for LGW, the IP address would actually stay on the HaloB itself. So once it does the DHCP request, the HaloB will receive the IP address assigned to that user, and it will essentially do a one-to-one map between the LGW IP address that it has associated with that user, and then to the actual RNTI or IMSI. So the user session, it would map those two. So the LGW IP doesn't actually get passed to the UE, because that's not part of the standard. So when the UE attaches to the network, it's still going to pull an IP address either from the MME or packet gateway. So it's getting its IP from the core network. But when you're having LGW, what will happen is it will get an LGW IP. In bridge mode's case, it would get assigned by the DHCP server, but it's not going to pass that IP address to the actual UE, right? Because this is local breakout features are something that's kind of outside of that standard a bit, but the UE won't know what that IP address is. So it has to do a one-to-one map between those IP addresses. Okay. Okay, so if you were like a first-time user of the Baicells product, this would be one of the first steps you would take, would be to create an account with the Cloud Core, and then from there you can get your cloud key. Your cloud key is then used to either enter into HaloB, or you could manually import or onboard your devices into your Cloud Core account, and this is where you would activate and manage your IMSIs as well.
Hey, Jesse.
Yeah.
Sorry to interrupt. We did get a question. The question is, we had a problem with the UE's IMSI. The last 4 digits are the same. So they provided an example where the last 4 digits were the exact same, like 0003.
Right. So that is one of the potential limitations with NAT mode here. Yeah, so if you have a wide range of IMSIs, there is the potential, not as likely, but especially this is more or less designed for like fixed wireless, right, for the LGW mode here. So normally for the fixed wireless ISP, you know, they'll have IMSIs in a certain range, and it's usually not as likely that you'll get the last four. So now if there are IMSIs that, you know, by chance have the same exact last four digits, it's not going to hurt anything. It's not like, you know, their traffic will be broken or anything. The only issue will be that you likely won't be able to remotely access them because, you know, they might be, the port forwarding might not be working correctly, or maybe one of them you won't be able to access. But, you know, their actual service will not be impacted.
Okay, thanks.
Yep. Yeah, I mean, again, the most commonly deployed is going to, or mode is going to be the bridge mode here, right? You know, you won't have that issue at all with bridge mode. Okay. We'll move on. So again, if you're a first-time user, you know, you would go to this URL here. Actually, you know, another shortcut is just cloudcore.baicells.com. Would also redirect you to this page. And you know, you just have to look for a sign-up link. Once you click the sign-up link, you would enter your information here, and you'll notice that a unique cloud key would be associated with that account. So once your account is created, that cloud key here is how you can onboard your equipment, and we can go into details later how that works. Okay, so yeah, once you fill out the form, you would get a email address. You do have to click this link to activate the account. So yeah, so even you fill out the form, you know, again, you have to, you know, look for the email, you know, check your spam just in case, but this URL has to be clicked before the account actually gets created. Okay, so that's, you know, again, that's already, you know, publicly hosted. It's easy to access. Now, if you had a local EPC from us, you know, we provide, you know, one-use servers, and we also provide for the OMC and BOSS as well. You know, so usually if you're purchasing the EPC, you'll get the full suite for the OMC and BOSS as well. So the OMC is our EMS. That's where you would manage the equipment itself, so the ENOBs, the CPEs. That's where your KPIs would be viewed from. And then the BOSS is for managing the SIM cards, essentially, right? So that's where you manage your subscribers. If you already have an EPC or third party, and you know, then at that point you'd be just looking at the OMC portion for managing the equipment. So again, for like, you know, details as far as what the options are, you know, that's something I think the sales team would be the contact there. Okay, so for HaloB, we do have two different modes. This particular image is kind of showing what we call our centralized mode, which is the default mode. So with HaloB, what we tried to do is simplify it where it's just a toggle switch. So you would enable HaloB, but your actual administration, procedure, steps, nothing changes. So what would happen in centralized mode is the ENOBs themselves, they would actually, you know, you would have your cloud key entered into the base station so it knows what account to pull from. But what would happen is when a UE attaches to the eNote-B, it first checks its local HSS database. If the IMSI does not exist, it then will query, again, there's no S1 connection at this point, so it can't talk directly to the HSS. So what it will do is it will piggyback off of the TR69 connection to the OMC, and then the OMC will then query the BOSS, which queries the HSS, which verifies, does this IMSI belong to this operator? If so, download the IMSI to the base station. So, so using the centralized mode, you don't have to change the way you do anything. You're still using the Cloud Core interface. You're still using the OMC portion, the BOSS portion to manage your SIM cards. So, from customer viewpoint, if they were already using the Cloud EPC, they switched to HaloB, their process as far as how they manage their SIMs did not change. Okay. Yeah, and this is, again, the centralized mode as we kind of discussed here. And then there's some screenshots down here. You can see it's just a toggle of enabling. So once you enable HaloB, you can see centralized mode is selected. You would save, reboot, and that's it, right? At that point, you're running the local EPC embedded into the eNote-B, and it would be pulling any new IMSI information from the Cloud Core account, using your cloud key and using the TR69 connection there. Okay, let me go. So I don't see the other slide. So there is one other mode that I don't think is in this deck, but there's something called HaloB standalone mode. So in the HaloB standalone mode, you would this is more of a manual configuration, but in standalone mode, you would download a template from the eNote-B and then fill in all of the IMSI information, so the key, OPC, all that information from the SIMs, and then you would import that back into the eNote-B. So that's kind of the difference. So a standalone mode, you'd have to, individually, one by one, upload your SIM card, information into the base station. But for centralized mode, it's automated. It automatically downloads that information, from the TR69 connection to the Cloud OMC. So yeah, in summary, those are effectively our three solutions here. Again, Cloud Core is the default configuration in any base station. So if you had a local EPC, you would need to, either way, you'd have to just change the settings, right, to point to your MME IP address, enter your information. It's, everything actually can be done from one page as far as the configuration goes. But you would, just change the configuration to point to your local core. If you are using HaloB, you'd have to import the license file and then enable the HaloB switch. Okay, so that is it's kind of a brief, but it reviews some of the mainstream eNote-Bs, CPEs, and our core network options. Again, not too long ago, that was the core network side was probably the most expensive and the biggest kind of roadblocker for anyone to deploy their own private LTE network. Now it's very easy. We kind of remove that complexity by using the Cloud EPC or HaloB options. So at this point, there's not that huge CapEx that's normally required, when deploying LTE. So with that, I believe we have a break upcoming, and you know, we kind of went through that section a little bit quick, so I guess I'll, you know, leave it up for Q&A for a little bit for now. So
Sure
yeah, any questions?
Let's see. I could potentially unmute our audience here. Try to do that if anybody has any questions.
Yeah, and depending on how much time we have, you know, after this last section here, you know, if we have quite a bit of time left, I think we could do maybe a quick demo as well, because a lot of this is, you know, like just high-level overview data. But yeah, you know, I'm thinking we could probably do some basic configurations, show from some live equipment we have here at the office. Just give the general feel of what it would be like, you know, for the initial configuration.
Definitely, that sounds great. I'm not seeing any questions come in through chat. Oh, here comes one. Cat 15 UEs would be with which antenna gain? Are there close range provisions for 4x4, 8x8, and superior eNode Bs?
Okay.
So kind of two questions there.
Yeah. So our Cat 15, right now we just have some samples. We're running some trials. The current antenna gain is 18 dBi. And this is, now obviously it will depend on the band used. The particular one we're testing right now is 3.5 gigahertz for band 48. So that's an 18 dBi. Obviously, if you have something like, you know, band 41 and 2.5 or lower frequency, the gain will be reduced. But for 3.5 gigahertz, it's a 18 dBi antenna. It's 4x4 MIMO, and actually that's, you know, for our kind of future base stations that we're currently testing, you know, they're operating in 4x4 MIMO, and so that's, you know, the configuration that we're currently testing. So hopefully that answered. I'm not sure.
We'll let you know if the question comes back around. We got another one here. Is HaloB centralized mode compatible with non-cloud Baicells EPC? So is the HaloB centralized mode compatible with non-cloud Baicells EPC?
Yeah, there is. So first of all, the idea with the HaloB is that there is no external core. So what could be done is, because it talks to our OMC and then BOS to get the SIM data, and then BOS connects to the HSS. Now there is a mode or configuration option where you could deploy the OMC and BOS, say, say that could be a local co-located install that we could provide. So we could provide the OMC and BOS, and then HaloB centralized mode could be used on someone's private network, and there would be no requirement for, you know, a core at that point. So all the SIM data would be entered in the BOS, you know, so the BOS would actually be saving all of the SIM card information. So the BOS is kind of like the subscriber database at that point. And then, yeah, again, all that information would get pulled into the Bs, and then, you know, they would be having the actual HSS MME elements to authenticate the subscribers.
Okay. Not seeing that come back around. Oh, wait, here it comes. Thanks. In order to mitigate local connection outages between eNodeB and BOSS, which is what I was referring to as a central EPC, not accurately, apparently. Thanks.
Yeah, if someone was looking to completely remove any, you know, like remote connection requirement, you know, whether it's the S1 connecting to wherever the EPC is located, or whether it's the TR69 connection to the actual OMC itself. If someone's in a certain scenario where it's ultra rural, the reliability is maybe not so much there, you know, I would suggest at that point using HaloB, but use the standalone mode, because you could just directly import the IMSIs there. So, you know, once you manually update the HSS on the eNodeB itself, at that point, there's no requirement at all for any kind of connection. You know, you could unplug the backhaul to the eNodeB itself, and it would still be, you know, all the users would still remain connected on the radio side. So that is the most robust and reliable solution at that point.
Okay. I'm not seeing any other questions, but if there are, please feel free to put them in the chat there. We can discuss them a little bit further. It looks like we're running a little bit ahead of schedule. Is that correct, Jesse? Yeah,
it looks like about 20 minutes. Yeah, if there's no further questions, maybe we could take the break now, and then, you know, 30 minutes, right? So come back at 10 after, and then we'll do section 3, and then if we still have some extra time, you know, we could try to do a quick demo at that point.
Okay, I think we should probably keep it to about a 20-minute break.
That works too, yeah.
All right, so we'll be back here at 11 a.m. Central. That's 12 p.m. Eastern. And we'll pick up at section 3, and then we'll wrap this up, and then hopefully we'll have some time for a demo at the end.
Sounds good.
Okay. If anybody does have any questions in the meantime, feel free to enter them into the chat, and we'll try to answer those when we get back here. Otherwise, we will be back in about 20 minutes. Thanks, everybody.
Okay, you can see everything fine now?
Yep, looks good.
Alrighty. Okay, so now we'll start looking into the weeds of it a bit, see how the configuration workflow, you know, what the basic settings are. We'll try to point out, you know, pretty much as high level, but, you know, what the initial steps are as well to get an eNodeB set up. But, you know, for us, we have a web GUI for pretty much anything, so it should be, you know, pretty straightforward once you become familiar with the LTE terminology and what the basic parameters are. It is a fairly straightforward process, and if you're using the cloud EPC, again, you could have it zero touch, and as long as it has internet, it can go active. But we'll review some of the main settings here now. Okay, so before we get started, we'll kind of review the differences with some of the products. So we touched on some of the 3 main single carrier products. I do see two that aren't listed here. We also have a NOVA 246 and 249 that are quite popular as well, mainly with the FDD bands. So those would be a 2 by 20 watt or 2 by 40 watt base station. So to review kind of what the numbers here mean for those that maybe aren't aware, so when we have the NOVA as our brand name for, pretty much outdoor base station. So the first number is going to be the number of ports, and then the next two digits is the total power in dBm. So our 2 by 250 milliwatt would be 500 milliwatts total, which is 27 dBm. So that's our NOVA 227. And again, we have a NOVA 246 and NOVA 249 as well. And there's a number of other custom products as well. But this slide's kind of taken from the U.S. market, where the 246, 249, aren't as common. But I do know for our LATAM market, especially where a lot of FDD bands are used, the higher power radios are quite popular as well. Okay. So again, our single carrier products here, they're 2 ports, so you would simply add a 2-port antenna. For the 436Q, you have a little bit of flexibility. It's 4 ports, so you could either deploy 2 2-port antennas if you're trying to do like a dual carrier or a split kind of antenna design, and then a 4-port antenna if you're trying to do any kind of carrier aggregation. As I mentioned before, for some of these features are licensed. So for HaloB, you would need a software license to enable that, and the same goes for the CA or DC. So if you have a dual carrier base station, but you don't have any license files added, it would only operate in the single carrier mode. Okay. So this would be the general workflow as far as, from kind of the unboxing to the connecting the cables, powering the HaloB up. Generally there's going to be, it's kind of optional if you're using Cloud APC, but for the most part you're probably going to want to configure what your frequency is, what your PCI is. There's going to be generally some basic parameters you might set, and then of course if on the network side, if you're doing static IP assignments, things of that nature. So normally you would have some basic configuration, or maybe you have some kind of golden config file you like to use. There's not a whole lot that needs to be changed, but you would make whatever basic change you're looking for, reboot it. At that point, when it comes back, assuming it has connection to the core, the cell status should eventually show up as active. One thing on the GPS antenna here, so we do include GPS antennas with each base station. Now the 227 is the one that has the GPS antenna integrated. So for the 227 product, there's no external GPS. For the other products, there are, but they are included. Now, you could, in theory, run without the GPS, but it, of course, is not recommended for the actual field deployment. If you do not have synchronization, you're going to cause interference to any neighbor cells. So, of course, GPS is going to, most likely going to be used for the outdoor deployment. But if you're just trying to do some, say, lab testing, on the bench configuration, it's not necessarily required. But And then we do have a mount that's on top of our base station for where the GPS antenna would be installed to. So generally you'll have that kind of prepped ahead of time before actually doing the installation. So yeah, you'd attach a GPS antenna, start the install, connect the RF antennas, the cabling, the grounding. You know, it says attach Ethernet, but depending on the model used, we can support either Ethernet or fiber. Either is generally used. And then, of course, from the installation, from the installer viewpoint, they can check the LEDs, make sure that the HaloB is getting powered. And at that point, you can then log into the base station and verify the configuration, make any changes if needed from there, and then check the status. Okay. Here is a close-up of our 436Q. So you'll see that they're N-type antenna connectors, and they're labeled from antenna 0 up to 3. So if you're using this base station, know that the antenna 01 is one cell, and then antenna 2 and 3 would be the second cell. So depending on the configuration, if you're doing split mode, you know, you just have to make sure that you're not crossing the cables at all. Okay, so on our base stations, you will see that there is a side cage for where actually all the cables run into. So this will be your backhaul and your power, and then there's some grounding nut at the bottom of the cage as well. Okay, this is kind of the LED chart. Obviously, you want to make sure the power LED is running. It should, you know, it should display green for cell 1 and 2 once those cells are active. And if there are any issues, the alarm LED will flash red. Okay, so this is an important IP to remember with all of our equipment because our HaloB and CPE have the default IP address of 150.1. So, and the username password is pretty easy, just admin. When you plug in the HaloB to the network, you could either plug it directly into your computer and then just reach it by static IP. But the HaloB actually has two IP addresses. One is for this out-of-band management IP, which is the 150.1, and then the other is the actual, what we call the WAN IP. By default, it's set to DHCP client mode. So if you didn't want to plug in directly to it and make some configuration changes, you could just simply plug it into your network. And if you have access to your DHCP server, you could look at the leases and see what IP address got assigned to it. And once you know the IP address, you could just enter that IP address in your web browser instead to get to the HaloB. For the Cloud Core URL, so this is for the management server. This is the ACS server URL. So by default, it's already programmed to connect to, in the US case, this would be the URL here. If you had either a local OMC or maybe you have this third-party ACS server, you would enter that URL in here instead. And that's on this, this is a screenshot here showing the management server page. So it's under BTS setting management server. Here there's a box here to enter or to change, if needed, the management server URL, which is your ACS URL. And if you're using our Cloud Core, you would enter the cloud key. Now, if you remember, let me try to, okay. So if you remember on the sign up page, there is a cloud key that was assigned to the account. So this is going to be your cloud key. When you log into the Cloud Core account yourself, you will also see that there's a cloud key in the top right corner, I believe, will be listed there as well. So you can log into your account, see what your cloud key is, but there is a unique cloud key assigned at the sign-up portion of the account as well. Okay. And by entering this cloud key, what that's doing is when HaloB sends the inform message to the OMC server when it's checking in, if the OMC sees the cloud key listed, it will automatically onboard the HaloB to your account. And at that point, it would be listed in your OMC account. Okay, so if you don't want to use DHCP for the WAN settings for the HaloB, you can, of course, change this to static and just simply enter your static IP on the network page. I guess one note here. So you'll notice on the network page we have your WAN and then you have your LAN IP. So as I mentioned, there's 2 IP addresses on this base station. So really this address 150.1, I think it does normally let you change it. We recommend you don't because if for whatever reason you forget the IP address to the unit, this is kind of the default out-of-band management IP. So it's, if you just leave everything the same as default, then in cases of emergency, it's easier to get to. You don't have to try to remember what this IP is either. Okay. So this is the LGW page. By default, this is set to on and it's set to NAT mode. It's on by default because, again, the Cloud EPC is enabled by default. And enable for Cloud EPC to work, this LGW, which is the local breakout function, also stands for local gateway. This has to be enabled for the user traffic to flow onto the local network. The Cloud EPC does not allow for user plane traffic, so it would just block it. So this has to be enabled for it to work, but it's already there by default. So again, the most common mode, this is where you would actually go to change it to the bridge mode, which is what we see as being the most common, but you could leave it in NAT mode, it will work just fine, but you can change the mode here if desired. If you have a local EPC and you don't want to use LGW, you just want to send all the user plane traffic to the core, you would need to disable this, which is on by default. So you would just disable this function here. And this is under the network LGW page. Most of the parameters, however, can be found, or the important ones can be found under the quick settings. So the quick settings, actually, the second page here, basic info being like we'll list, it's your first overview page. But quick settings will have pretty much everything you might need to change as far as your frequency. If you have a local core network, maybe you need to change your PLMN and your MME IP address. These are already filled in by default for the Cloud EPC for US. So if you were a Cloud, core customer, you would really not make any changes to this page other than perhaps the frequency, which for your ERFCN, you could adjust that here. You can adjust your subframe assignment, so your timing, so what TDD, and this is TDD, right? So in this case, you would change your TDD settings, so your subframe assignment and your special subframe pattern. 2 is the most, I think, common used, but we do see subframe 1 is also, used in some cases, especially where uplink is more of the bottleneck. But for the most part, the main things you would change here are the ERFCN for your frequency, if it's a different band, of course, you know, your bandwidth, is it 20, 15, 10, 5 megahertz, your PCI would be changed here. Again, as Yen was discussing in the first section, you do not want the same PCI used for any neighbor cells on the same frequency. Technically, it doesn't matter if they're all different frequencies, but you do want, you know, at the bare minimum, you know, do not have any overlapping PCIs. And then the cell ID, this also has to be unique, but we do make this easier with our equipment. So out of the box, this number is already unique because it's based on the MAC address of the HaloB. So you shouldn't have any kind of you know, collisions with the cell IDs. What would happen is if you have the same cell ID with another HaloB on your network, they will be fighting with the MME and constantly disconnect. So that does have to be unique. But again, with our HaloBs, that's already automatically generated and should be unique if it was only Baicells deployed, because again, this is already generated and based on the MAC address of the HaloB itself. So it should be unique. But if you had your own cell ID planning, ECI planning, this could easily be adjusted here. Okay. So you'll notice the cloud EPC, there is a switch here. This should be on by default, but if you had a local EPC, you would just simply disable this and then make whatever changes necessary. So for local EPC, the main things you'd be changing is your MME IP, PLMN potentially, and then TAC, tracking area code here. Normally one works, but depending how your core network is programmed and what TAC kind of you're using, you would potentially change that. But MME is most important, and of course PLMN if you have a different PLMN. Okay. So if you have a dual carrier base station, one that can support CA or dual carrier, there is a carrier setting option here where you could just simply select from the drop-down list of what carrier mode you want to be in. Okay. So as far as the main overview page that's listed over here, the main thing that you really want to pay attention to is the cell status active? If the cell status is active, the HaloB is broadcasting and users can attach. If it's not active, then there's no transmission happening, and either it's still booting up, maybe it's still synchronizing, or there's some configuration error or connection issue. But of course, the most vital thing is the cell status active or not? And then some additional notes on this. So when the HaloB is powering up, the steps it takes, firstly it's going to take a couple minutes for the software to boot up. And then it will start the GPS synchronization procedure. So if you were kind of quick to log into the HaloB before it kind of is like fully starting up, you would notice that the GPS sync status, it will probably say synchronizing because it's still trying to synchronize. That process could take, another potentially couple minutes or so. Once the synchronization is complete, it will then say synchronized. Now, the MME status cannot be connected until the synchronization is complete. So the procedure normally is if you're using Cloud Core, so one, the IPsec needs to be connected. If that's not connected, there will be no connection to the Cloud EPC. But generally, there's not too many issues there. But if that would be one potential issue if the IPsec is not connecting for whatever reason. But the main thing is GPS synchronized? Because if it's not synchronized, the MMEs will not connect, and then the cell cannot go active. As soon as the MMEs are connected, it's just a matter of seconds usually before the cell status will flip to active. Okay. So this is the B web GUI itself. To the right here, at the bottom here is a snapshot from the OMC. So it's kind of showing, what the view from both software looks like. Okay. So here is some kind of pages. This is actually from one page. It's just trying to summarize this up. But again, when you first log into the B, this is the first thing you will see. You will see this basic info page. If the cell is active, you will get some other kind of results underneath as well. So it will then display your radio resource usage, which tries to summarize the aggregate PRB usage as well as the blur. It will tell you how many users are connected, and for the UE status, it will give a kind of overview list of all the IMSIs that are connected. It will list their IMSIs. If you're using LGW, it will list the LGW IP address, and then all the other basic metrics. Again, for the quick settings page, we kind of already overviewed this, but this is where you would make any changes, to the frequency, potentially if you're using TDD, any kind of TD config. And then if you have a local core, you would make changes to the MME and PLMN. And of course, you want to make sure the PCIs are unique to any neighbor cells using the same frequency. As far as TDD synchronization goes, I think this is laid out here, but you want to make sure that whatever you decide on, if you're using config 2 or config 1, you just want to make sure that it's pretty universal across your network to avoid any kind of overlap with the downlink and uplink subframes. So that of course is important. So that's one thing to note. Okay. Don't need to talk too much on this. There's a lot of basic pages within the B. This particular one would be where you would change the NTP settings. So NTP is used whenever there isn't the GPS synchronization. So when you're looking at like your B log files, the timestamp should be based on GPS. But if the GPS wasn't synced, then the NTP sync, timing would be used instead. Okay, for the upgrade and backup page, this is simply where you would upload any new firmware files that you might have. You can download the log files here as well. So for troubleshooting, this page is used to capture any kind of log files. Your config files are here as well too, so you can download and restore configuration files on this page as well, or on the backup and upgrade page. There's a diagnostics page which has some basic troubleshooting tools such as ping and traceroute. And then under the LTE, there's a sub-menu of pages. So we'll try to cover, now some of these might be model specific. So So we have essentially right now we have two chipsets that we're using with our HaloBs. We have the Intel chipset and then Qualcomm. So depending on the model and the chipset used will kind of depend on what sets of features are available. So, we might see or discuss some features today that might not exactly be on, every model. So just keep that in mind. For the mobility parameters page, this is where you would set your A1, A2 such events. So this is really for like handover configuration and is really only used if you're going to have a local EPC. The cloud EPC, HaloB, they do not support mobility. So this would be a requirement, for the local EPC. On the advanced page itself, it does have a bunch of more advanced type features. Some of them to point out, so one here that's highlighted as working mode. We can change how many users are supported on the base station. So, it really depends on the model. So, like if it's an FDD, say Nova 246 or 249, I know we can support up to 256 users, and then other models might only support up to 64. So it just depends on the model that's being used at the time. But there's other settings here. One of them might be so one's called multi-element. So if you have a bunch of VLAN configurations, you could set what your user plane traffic, your control plane traffic, your say your tier 6.9 traffic. You can actually set that to use different VLANs. So there's a little bit more advanced feature sets here. You can change your scheduler. So like if you don't want to use RR, we have PFS is another one. But also depends on the model. But there's some more advanced, I guess, features here that aren't required or needed to be changed, but they can be depending on what is done. Random access parameters, there's actually some importance there. If you're going to do any kind of frequency reuse, we already discussed about PCI, but there's other settings here that you would potentially look to adjust as well. But we're not going to dive, I think for the purpose of this training isn't to dive too much into all the details, but mostly just to review what the main requirements are and configuration is. Okay, so this is one of those features that's available on the Intel platforms. Because with Intel, we can read the IQ level, something we can't do exactly with Qualcomm. But this is one of the features on some products where we do have a built-in spectrum analyzer. So it is helpful where you will configure it. It will be basically using the LTE stack, but it will be reading the IQ data in all of the uplink subframes. So you can see if, if like the first uplink subframe looks clean, but the second one has noise, that there's potentially, for example, there could be some timing issue, maybe the wrong configuration used, or some other neighbor base station out of your controls on a different config. But this is helpful if you're dealing with, performance issues and trying to narrow down what potentially could have some interference or not. Yeah, also, and this was also another Intel feature, but we can see the uplink PRB RSSI. So this is also another noise kind of indicator to see if it is running outside of spec or not. So you'll see that there's like a line around -118. So that should really be the baseline of the noise here. In this screenshot, you can see it is quite noisy, so there's definitely some interference on the bottom picture here. There's always going to be a little bit of noise in the very middle, because this is where the PA is at. So the PA does have some slight noise, in the very center channel. So the middle bump can be ignored, but the rest of it should be around this line. Okay. Next, we'll go through the CPE, not spend too much time, because honestly, with LTE, the CPE is very simple. The only true requirement is that you insert the SIM card, right? Because on the LTE network, the SIM card is what authenticates that device to the network. So it's not, as if maybe you're using Wi-Fi CPEs, you have to know the passwords, the SSCIDs, you have to know the frequencies potentially. So this LTE is much easier. The installers just need to insert the SIM card, and honestly, that's really about it. Maybe just change the password on it. There's not too much to it, but depending on if there's some maybe more advanced settings or configuration needed, we can kind of point some of that out. So here is the first overview page of one of the CPEs we have. Looking at the part number, it looks like this is a Cat4 CPE here. So here we can, see the basic RSRP. This is Cat4, so it only has 2 antenna chains. Cat6, you'll see 4 lines here for all 4 chains. There's a signal screen button, so if you're trying to do alignment, you could click that. It'll bring up another pop-up, which will refresh the page quicker when you're trying to really do, align it into the strongest signal possible. And then under the LT status, you will see some other basic or the common metrics that are important. One, you'll verify that you're connected to the correct, PCI or cell ID, so you're on the right cell. And then, the MCS levels will help indicate, the modulation, which ultimately is really the importance here, because your modulation is kind of going to dictate what your throughput capability is. So in this case, obviously, I believe this screenshot's taken from the lab, so this is, very close range. So we can see the RSRP is very strong here. You normally won't see this kind of level of strength in the field. And then SINRs are pretty much maxed out at around 30, and MCS levels also maxed out around 28 and then 22. But
hey, Jesse, we did get a question. Would it be possible to go over the eNodeB scheduling algorithms in more detail?
Yeah, we can touch on that. Actually, let me run through this deck quick, and then I'll try to bring up one of the lab units here. We don't have a slide that goes into the scheduling details right now, but depending on the model you have, like with the Intel products, we have right now the RR, which is every product has RR by default. It's a round robin, so it's just first come, first serve. We see that's common even in the tier 1 markets. So it's normally actually not that changed, or it's not changed very often, but PFS was another scheduler. I don't have a slide on it, but essentially with PFS, it will take into account the signal strength, the CQI essentially, and it will also weight that against the historic throughput for that IMSI. So it tries to have a more fairness scheduler, but also at the same time trying to give priority to the better connected subscribers. So that would help boost the aggregate throughput of the base station. So if the better signal customers are getting higher priority, they get, they have higher modulation, so they can transfer the data more quickly and at a faster rate. So the aggregate throughput should go up, and you can adjust it. We have like this 0 to 100 scale, so you can kind of set how much weight you really want to put towards the PFS logic, which is taking into account the customers with the best CQI. But what PFS does to try to offset the abusive users is if the user has been using a lot of data, it will, kind of punish them a bit, and so it will not give them, as much priority, even they have maybe very good CQI. So that's something we actually just recently introduced. So we not too many customers are using it just now, but again, RR is generally pretty good for, for overall, most use cases.
Great. Thanks, Jesse.
Yep.
Did get one more here. Is it correct to say that RR equals PF with 50%?
I'm not. There's no logic really other than the first users to request data or request a resource. They get scheduled, immediately at the queue, wherever the queue sits, right? So, yeah, there's no really, it's the most simple logic because it's just first come, first serve. So, yeah, but obviously the impact of RR is if you have a lot of cell edge users, they could bring down the total performance of the base station, right? Especially if they're abusive type users.
Okay, that seems to have answered the question.
Okay, I'll move on. So this is kind of at the bottom of the overview page, but it does show where you can see the APN IP address, which is assigned by the core. So this is important to point out that if you do have LGW enabled on the base station, this IP address will not be the LGW IP. So again, that LGW IP will reside on the B and then map that IP to the address here that it actually has. If you have a local core, you have full control over the IP assignments, and you normally would not use LGW if you have a local core. But yeah, and then we can also support up to 4 APNs here. So so the only time you might really make any change on the CPE configuration-wise is if you want to configure multiple APNs. Why you would configure multiple APNs? Normally, what we see with fixed wireless, with those with local cores, they might configure at least 2 APNs, where one is used for the management, so they can access the CPE from one APN, and that IP is used by the CPE for like SNMP and TR69. And then the second APN is used by the actual user, where that APN gets bridged, and so that whatever IP address that's assigned for this APN will sit on the customer router behind it. So that's a configuration we see used as well. Not required. You can still do everything over one APN, of course, but you do have the ability to configure multiple APNs here. We also have layer 2 support. It depends on the CPE model of what layer 2 protocol is used, but for the Cat4, we can support the VXLAN, and then for the Cat6, we support GRE. So if you have our EPC, we already performed this integration of having GRE and VXLAN server or endpoints built in to the EPC itself. So we do have our own end-to-end solution. So if you did need layer 2 support, you could pass an IP, from the other side of the EPC all the way to the device behind the CPE. Because in LTE, the packet gateway, wherever the packet gateway is residing, wherever the core is, that's a layer 3, route. So if layer 3 is not able to meet the requirement, then layer 2 could be used, which essentially builds a tunnel, another VPN tunnel, between the two endpoints, between the CPE and within the EPC. If you are using SNMP, it's not enabled by default, but can be configured here. You'd have a lot of the basic pages you would expect, be able to do firmware upgrades and restore configuration to default, and download and upload config files. Again, basic troubleshooting tools with ping trace route as well as iPerf is on this page. Yeah, I think that covers, again, on the CPE side, there's really not too much that's required or mandatory. So, so it is possible that it's just a SIM card, insert, and that's about it. We do see some operators might have their golden config file. They might upload to the CPE first. Maybe there's a standard password. Maybe they did have APNs set up in a certain way. Maybe SNMP is already enabled, and so if there's a certain set of default settings that's preferred, a config file could be used as well. Okay, on to the OMC side of things. If you're using the commercial cloud core, there is a billing element to it. For us, it does cost $1 per active SIM card per month. So when you do sign up and create the account, it will require a credit card to be entered. And that gets billed automatically every month based on how many active SIM cards there are. Now, if you have your own local OMC environment, obviously this is not a function there, but for the commercial cloud core, we do charge at that rate. Okay. When you first log in, though, you'll see the dashboard, which tries to summarize, how many alarms there might be, gives a quick overview of your aggregate throughput across all your Bs, just a quick snapshot of the network, really. It does make it easier from that page to just click on, like say you had 4 critical alarms, you could just click that and then bring up the alarm page and see what could be going on. And there is a notification section. I believe that's in here later, but you would want to, it's an email notification right now, but you would want to configure that with the appropriate email address just to make sure that these alarms are being sent, and so you don't have to keep checking OMC all the time. Okay. When you're on the alarm page, you can, click the little ellipses here to bring up either the details if it's not maybe quite understood what the cause print here is. So it will give a kind of details, a little bit more detail there. Now alarms should automatically clear. There are a few alarms that maybe don't clear on their own. But so if the issue is already resolved, you could just, or you just want to ignore it, you could just clear the alarm or confirm it. But for issues, say like there's a S1 disconnect with the MME, those alarms will clear up on their own, once the issue is resolved. So yeah, there is if you can see here, there is a notification, again, page where you can enter your IP address. The library just simply shows, if you're curious what each alarm ID means, and, there's more details listed there as well. On the dashboard, again, has a quick overview of the network, highlights some select KPIs, mainly, how many of your ENOBs are active compared to potentially inactive, number of CPUs connected to the network, and so forth. Okay, on the ENOB monitor page, this will list all of your ENOBs. You can see the different settings and status for each one. And for every ENOB, you can also click the little ellipses and get more detailed information or configure the settings. So there are certain settings you can configure right from the OMC. You wouldn't have to log into the ENOB itself. But you can, again, you could click like the ENOB, you can go to information. On the information page, you can see there's some stats you can see, alarms, logs, any license information. But if you're trying to narrow down like alarms to specific ENOBs, you could just bring up the ENOB information page, click on the alarm section, and see not only if there's any active alarms, but it's helpful, you can click on historic alarms to see what is all the alarms from the history. If you did collect any log files, those are visible here as well. There is something called device exception log. So if the ENOB was to reboot for any abnormal reason, maybe there was a software crash, if there's some bug, it just restarted on, randomly on its own. If that was to ever happen, the ENOB will automatically upload the crash log files to the OMC, so those can be visible here as well. Okay. And again, you can make some setting changes on the ENOB. You could change the ENOB's name, and a lot of this part's grayed out because in this particular screenshot, it looks like the ENOB is offline. So you cannot change much other than the name of the ENOB. But yeah, if it's online, you can make setting changes, just like on the kind of like the quick settings page of the ENOB, you can make a number of changes like to the frequency and so forth. Other options, you could collect logs from the ENOB, you can reboot it. There's also a toggle here for enabling HaloB. So on the ENOB, you saw there's a drop-down box to enable it. You could also enable it from the OMC as well. And another thing you could do is you could manually deactivate it or turn off the RF. So if you're, trying to troubleshoot or, for whatever reason, you could make those setting changes here as well. This is just the reset password page, so it is possible to change, whether you forgot it or maybe you want to do a mass update change to the network. You can do that with the reset password page. This is the maintenance log page, so you could schedule log collection tasks. So again, this can be done on the ENOB monitor page, where you would click on the ENOB and then click on logs and collect logs. So you can either do it individually from the HaloB monitor page, or you could just create a task from the maintenance log page. And one kind of nice feature is for the logs that are downloaded, you can view them and you can actually like open up the actual files and see them within the OMC. So there are certain files within the log files that are pretty important if you're trying to troubleshoot, such as the syslog and the debug log, and they will print lines, based on either certain KPIs, or in case of the debug log, it does print plain text, all the events, so if there's an S1 disconnect, you can see, some of the messages in there. Okay, there is a software rollback feature. So if you upgrade it and determine that it might be software related, this could be something that's done from the OMC side to roll it back. Okay, then we have the register page. So if you recall, we had a cloud key. If you were to enter the cloud key into the base station or to the CPE, that will automatically onboard that equipment to your account. There's a second way to do that. The other way is that you go to this register device, and there's a plus button, so you could click the plus button and then enter the serial number. So you could just manually enter the serial number of your HaloB CPE, and that would also onboard it to your account. So those are the two methods to get the equipment into your Cloud Core or your OMC account. And then there's the license files. So you can if you say you purchased a HaloB license or a aggregation license, for example, you can import them into the OMC. So that's one option, and then associate it to the particular HaloB. So you either can do that from the OMC, or you can log into the HaloB and import the license there. So you have the two options from that side. Okay, then of course, can upgrade from the OMC. So you will have a list of the software files when you first go to the upgrade page that's available. You would click the Create Task button. So you can do a mass update if you wanted. So you can select which HaloBs you want to upgrade. You would then select which software version you want to upgrade to. And then you can choose if you want to, perform the upgrade immediately, or you could schedule it for a later time. There is a retain configuration option that's checked by default. So upgrading should not change any settings on the HaloB, but if you wanted a clean upgrade, you could uncheck that if you wanted, but it would require that you have to reprogram the HaloB after the upgrade. Okay, on the CPE monitor page, we can list all of the CPEs here. You can see, all of the metrics here, what's the MCS levels, RSRPs, so everything that you would, normally check. And, on the CPE and HaloB monitor page, you can actually click the gear icon, and you can kind of set what fields you actually want to display in the table, and you can, change the order of how they're displayed. So, yeah, whatever is important to you is kind of customizable as far as what you want to see. And there is one of those fields is called history, and they have a little chart icon. If you click the chart icon, for that particular CPE, you can get the charts, for, these different measurements. So of course this is helpful for troubleshooting, you know, so over time you can see if something changed with the radio connection and the throughput and so forth. As far as some of the settings you can set from the CPE monitor page, again, there's a little ellipses type option you can click next to every CPE, just like you could with the HaloB. If you go to settings, you can change the, you can configure a PCI lock or frequency lock. What we see with fixed wireless, especially when there's a lot of cells in a particular area, you might get to a point where you want to kind of force the CPEs to connect to a certain base stations. Maybe you're trying to load balance, or you just don't want the CPE to roam, you know, kind of connect to the wrong cell or undesired cell. So in that case, you could just PCI lock it to the correct frequency and PCI. There's a frequency lock as well. There's a few different settings here, but it's essentially a cell lock type feature. Some other settings for the CPE, if you're trying to do more than one CPE at a time to configure a PCI lock, under the maintenance page, PCI lock, you can actually do a mass update. So what this will do is, yeah, if you're trying to lock, you know, more than one at a time, you know, this would just be the method to do that. Of course, you can do a reboot task as well if you need to reboot multiple CPs. Register, this is the same as the HaloB. So if you didn't use the cloud key as a way to get the hardware into your account, then you would use the register device method to just manually enter the serial number. Of course, we have upgrade from OMC is there as well. Can do more than one CP at a time. Keep moving on. Okay, there's an alarm view page. You can kind of customize that as far as you know, which alarms you want to see or filter out from. You know, sometimes maybe the alarms are a bit noisy, or you're just trying to narrow down to a certain view. So it is customizable as to which alarms you want to see, or what type of alarms. Kind of already discussed you know, the notifications where you would set your email address. And you can also set as to what type of alarms you want. So if you don't want to be notified for just you know, minor type alarms or warnings, you can filter that out so the alarms don't get too noisy. And then this part's not covered as heavily, at least for this training, as this is a US specific feature set. But for CBRS spectrum, it does require connection with the SAS to authorize the transmission within the band. So this is our SAS feature, where the OMC will act as the domain proxy to connect to the SAS. But here you would just set what SAS vendor you're using, enable it, and then at that point, you would enable SAS on the CPEs and the HaloBs as well. Okay. And for each device, we can see the different stage as far as where it's at with the connection to the SAS, with the last stage being transmission mode, which essentially provides the authorization. Okay, and I guess the last page here we have is the security section. So there are different user groups you can create that have different level sets of permissions. So if you only wanted, so you can add multiple users, into your OMC account. If you just wanted, certain view-only permissions, maybe with the accounting team, or you could change it so they can only view, and certain pages they can only see. Maybe they only have access to view the boss side. But yeah, it is flexible as far as what levels of permissions you would give certain users. Okay, so that is the end of our duck here. So I guess I'll first leave it open to see if there's any questions so far. And then if we have a few more minutes, I'll do a quick dive into the configuration of the device itself with the lab units here.
Sure thing. We don't have any questions coming in right now. Give it a couple more minutes, and then still do have an hour, so that demo seems like it would be a good idea, Jesse.
Sure. Okay. Can we take just a quick 5-minute break, and then I'll get things staged here a bit, and then I'll start sharing my screen for, yeah, just kind of overviewing some of the configuration we just discussed.
Absolutely.
Okay.
All right, we can be back in 5 minutes.
Yep. Version, would have the same limitations as the 243. So I think the answer is it depends if it's TDD or FDD.
All right. And then there was also a question asking for more information on the outdoor CPE, the ES7035W. I don't think we have that one available on the website.
There's no W that I'm aware of, but there's a 35E and a 35L. The 35E is the high gain 19 dBi CPE, that's Cat4. Yeah, I mean, the only difference between that and then the L being the 14 dBi. Now I'm defaulting to the 3.5 gigahertz frequencies because that's what's commonly used here in the U.S. So obviously that depends on the frequency, but yeah, there should only be 2 EG735 like shells, the low gain and the high gain. So yeah, and then of course, depending on the band is gonna, the specs would change based on that. But it's only a matter of one has a bigger antenna than the other.
Okay.
But it should be on the website, yeah. As far as I think we label it high gain. I don't know actually how we're labeling it on the website, but it should be Atom, ODO4 or something like that.
Yeah, if you can't find the information on the website, I'd recommend you work with your partner who gave you the information for that unit in order to find some more details on it. Another question, in order to reach a CPE in mode LGWNAT, what IP address do I need to introduce?
It would just be the same IP as the B.
Okay.
So yeah, and actually I can maybe start that right now. So.
All right.
Yeah.
Just before we jump too far ahead into that question, what's the maximum distance LAN between one CPE and the PC client?
Sorry, can you repeat?
Yeah, let me send that one to you in Slack too. What is the maximum distance LAN between one CPE and the PC client?
I don't know if this is maybe about between the PoE and the CPE, because the outdoor CPEs are powered by PoE, and they are the 24-volt PoEs. So there's, I mean, obviously the distance will be depending on, you know, how much that voltage can remain. So I don't know that we have any specific spec on that, right? But probably no more than 100 feet, if I had to take a guess.
Sure. All right, sorry. Go ahead. Seems to be everything is coming in right now.
Okay. All right, so this one is actually a Nova 233 that we have in the lab here. Just using this as a kind of example, the actual interface is going to look the same no matter what HaloB you use. So it should have the same looking web GUI. But here we will see that the cell is active, and then we have our UE connections down here. We can see, in this case, we're using LGW bridge, so we can see what the LGW MAC addresses are for each, you know, IMSI. So this IMSI is converted to the MAC address. This MAC address is used in the DHCP request. So this is the IP that gets assigned, but again, this IP sits on the HaloB, not on the CPE. If we scroll over, we can see the different stats here. You know, what TX power. So TX power, for those that aren't too familiar with the LTE, the TX power will vary on the CPE. It will dynamically change based on if it needs to pass traffic or not. In LTE, it's designed to try to keep the power as low as possible because normally the UE is your phone, right? So you're trying to reduce battery life. You're also trying to reduce interference on the uplink. So the TX power will drop. And right now we're in the lab and they're kind of right next to each other, so it's going to drop quite a lot when it's not transmitting anything. But we can get like instant kind of details. So right now we're showing zeros because there's no traffic. So if you're really trying to get a pulse onto what the actual blur is, what you'd want to do is for that particular user, you know, maybe run a speed test because then you can see what the actual updated measurements are here. If there's no traffic going through it, this can look kind of bursty and spiky, and it might not be as totally accurate. But yeah, it's better when there's actual traffic running through here. Then we can get a better, you know, idea of what the actual KPIs are. The path loss at the very far end. This is the signal strength on the uplink. So this is what the HaloB is seeing. You know. It roughly correlates to like the uplink RSRP, you know, about 3 dB off, but it gives you a rough idea of what the signal strength is on the up. But, you know, one thing that is difficult to monitor though is because the TX power is always going up and down, you know, due to LT spec. You know, the uplink MCS will also fluctuate because of that. So it's, you know, if you're trying to monitor, it's a little more difficult, right? If you're trying to track the history of the uplink MCSs assigned, just because they will move a lot, and that's the unfortunate nature of just the way LT works. But yeah, so I can, you know, on these IPs, you notice they're clickable URLs. So if you happen to have the remote web enabled on the CPE, we can click on the CPE and bring up the page. So here I'm connecting to its LGW IP address. So this is connecting over the air, over the LTE interface. And I'll just log in as admin here and can see, you know, again, this is in the lab, so they're pretty close together. and can see the different measurements here. And you'll notice that the actual IP address that the CPE has is different from the LGW IP address. Okay. So some of the things you might change, you know, maybe you have a different preference as far as what the network is. You know, normally this isn't changed, but yeah, just like the HaloB, the default IP is 150.1. You usually don't need to change anything here on the WAN side. Not going to touch that too much. This CPE that I'm connected to is an indoor CPE, so it does have Wi-Fi settings. So you can, you know, make any changes to the Wi-Fi if needed. I'll just point out some of the main ones here. So DMZ is sometimes used if the customer. So if you're only using one APN, and the customer, you know, is hosting, you know, their own servers, security cameras, whatever it might be. If they want to do their own port forwarding, you could enable DMZ. One common configuration I see is on the LAN side, you know, maybe they just assign one IP address, and then they would enter this one IP as the DMZ. So all the, you know, all the traffic would forward, and ports would forward to this one IP address. So that's kind of one trick to, you know, if they're doing port forwarding from the router, to make sure that, you know, it's accessible with whatever IP becomes assigned. And in this case, it would be, you know, NATed to this IP address, and then this is a private IP, so then it, you know, NATs to whatever the public is. So it depends on the network design, what's being, you know, source NATed, destination NATed, you know, would depend on that.
We did get a couple more questions. You might be covering some of this. What is the procedure to add an end monitor to the CPE connected to an HaloB? Normal questions.
Well, I'm trying to understand what end monitor means. We have SNMP, right? So this is a monitoring protocol typically used, you know, pretty standard on networking, you know, devices. But TR69, this will be programmed by default to the cloud. You would, you know, if you have a different OMC or third-party, you know, ACS server, you would enter that into here. And, yeah, that would make the CPE report to the management server. But, you know, additionally, SNMP could be used as well. So these are the northbound interfaces. So this is how they would be monitored. And then on the web setting, this should be enabled by default, but if you wanted to prevent remote access, I guess you could do that. But normally this is enabled to allow, you know, remote access, you know, from the operator side, so that they can also access the CPE remotely, just like we're doing right now.
All right. Another question is line of sight necessary for the first connection to the CPE?
No, yeah, you know, of course, it all depends on the, you know, the signal, right? So if, you know, even if it's in a non-line of sight situation, if the signal's strong enough to attach, which is going to be based on the RSRP, then you're fine. Actually, I can point out on the HaloB side, it's under, I believe, mobility parameter. So if you go to LTE mobility parameter, we can define the cell selection settings. So under here, there's cell selection. So this QRX setting, this is one of the, I believe, SIB messages that's sent during the broadcast. So this when the when the UE is doing its cell search, so you power it on, it's trying to search for a cell to connect to. It will, it will read from the broadcast messages of the B. So this is one of those broadcast parameters. So this is telling that any UE that sees that's decoding the broadcast message, it's telling it this is the maximum RSRP that is allowed to connect. Now, minus 60 is not the actual, you actually double this. So this would mean that it's 120, and then you would add this number, which would make it 119. So right now the setting is that if the RSRP is 119 or stronger, it can attach to the cell. Right, so it's not due to is it line of sight or not line of sight. It's just simply due to what is the RSRP. If the RSRP is at or better than the cell selection parameter here, then it can connect. Now in LTE, you can technically connect up to a negative 140, not recommended at all, but it could be changed, for example, here to minus 170. So then we can allow up to a minus 140 connection. But, this, I think by default it's pretty good because you normally don't want anything in the 120s or weaker attaching to your cell. It's going to really bring down the performance. But if you did require that, this can be adjusted right here. Maybe you make it a 30, maybe you just slightly adjust this to allow for a little bit weaker connection. But yeah, but again, it's going to be based on the RSRP.
Great, thank you. Oh, here's another one. What about reselection? How does it work? Does HaloB setup support it?
No. Well, so the HaloB, the built-in HaloB does not, these mobility parameters, again, you need a full EPC, to do these kind of handovers. So we do have in one market, we have something called a HaloB gateway. We have not brought it to the North America market yet, but there is it's basically the same as the EPC, except the MME would remain and HSS would remain in the B with HaloB, but the packet gateway and other elements are inside this HaloB gateway, which allows for handovers to take place. So we do have a product, we just have not brought it to North America yet, that can work with HaloB to do this, but yeah, normally these reselection and A1 events and so forth, this is going to be for handovers. This is going to be where you also add your cells, your neighbor cells here. But again, this for fixed wireless, you normally don't worry about any of this, and for the mobility handover purposes, normally you would use a local core, which is going to be required anyways to do that.
Okay. Yep.
Okay, if you recall from the OMC, when we were discussing that you can do like PCI locks to lock the cell, this is where you would do it from the CPE side. So by default it should be full band, it just searches it for everything and will connect to the strongest cell that it can find. If you wanted to lock it, you can do that here, like a cell lock, for example. You can lock it to whichever band, frequency, PCI. We could lock it to a particular frequency. We can also lock it to just a particular PCI. So there are ways to cell lock this, if that's needed. Okay. Then this is where you would configure your multiple APNs. And actually to do that, double check here. So if on the WAN setting, if this is set to bridge, you would save this first to bridge, and then on the APN management, you will have a new option that will show the bridge. So what we normally see done when people are configuring multiple APNs, they'll leave the first APN as the management APN, the default APN, and then they will program, maybe they have another APN name called internet, and this is, they would have a bridge option here, which will show up once bridge is selected, and then at that point, whatever is plugged into the LAN port of the CPE, it will grab the APN IP, so it just does a IP pass-through. So we do see that with some customers that want to configure multiple APNs. That's the most common setup that we see. But otherwise, just one APN works just as fine. Okay. We have some, if there is going to be some manual port forwarding that can be done here. A lot of this is typical security settings you would see with any other routers. There's some kind of other additional protection. You could enable that, but normally this page is not really adjusted or changed too much. The VPN side. So the one difference with the layer 2 for the Cat4 CPE is that the layer 2 can only be configured from the OMC. So this is the one thing that we cannot change directly from the CPE. So if you have a local OMC, the layer 2 function will be open, and so it will allow you to program, because there's a lot of back-end configuration that's needed, and they just never added the web support for this, but we can see right now it's not configured, so VXLAN server is not reachable, and but you would set the APN name and then what VLAN it would be associated to. But yeah, there's more details we could go into, but for this to work, it requires a local EPC, local OMC, so that's something we're not going to dive into right now. As mentioned before, we can, if you want to ensure that remote access is working, just make sure this is checked. It should be checked by default. Again, if you have local or third-party ACS or OMC server, you can configure the URL here. By default, it's already programmed to the cloud OMC for US. SNMP, if it's disabled by default, but if you wanted, you could enable that. And then if you were using CBRS in the US, there is a SAS page where you would enable that, enter the respective information to try to get registered. So I think that's the highlights on the CPE side. Let's go back to the ENOB itself. But as you can see, we can just click on the IP address, LGW IP, to get to that particular CPE. Let's see. We have SNMP on the ENOB as well. Let's go to the WAN page. Okay, so if you were to add different VLANs, so there's a VLAN table here. So if you were to add if you had a particular VLAN, whatnot, you can set that VLAN as the default interface if you wanted to not use the native VLAN. Here we have a static IP address set, and again, we can always access it by plugging into it directly and getting to 150.1, which is the default here. Okay. So with the Cloud EPC, this is all enabled by default as well. So IPsec will be enabled to connect to the MMEs. There's 2 MMEs, so there's 2 connections. We have West Coast, East Coast servers, and then we have the binding as well. So this is only for IPsec, for the most part just for Cloud EPC configuration, but if for your local network, maybe you had local EPCs that you're also using IPsec, then this would be set up here as well. But essentially here we're binding MME1 to be which MME IP address and then which tunnel. So this is kind of the MME pool configuration here. So essentially, once you have 2 MMEs connected, if one was to disconnect or go down, the HaloB itself would not be impacted. It would still remain, connected and active. So it does offer some redundancy there. And so again, that actually, before I move to that, one comment, if we go back, let's go to quick settings here. So quick settings, this is where, again, we would configure the frequency you want to use, the bandwidth. Now, the Intel products do have an extra subframe assignment. This is like for, I think, special kind of niche use cases. Maybe you're doing some surveillance cameras and you need more uplink. This is where subframe 0 could be used. But, normally it's subframe 2, maybe 1. You just have to make sure that, any neighbor cells on the same kind of band are using the same TDD config here, if you're using TDD. Again, PCI, you want to make sure this is unique for any base station on the network that's using the same frequency, or at least in the same area. Now, this Cloud EPC switch, it says disabled, but it doesn't mean it's not configured for Cloud EPC. All this switch does is if I enable it and save, it will reprogram the HaloB to the Cloud EPC settings. So if you made some changes, maybe something got messed up, or you set it to some other core and you decide later you want to go back to Cloud EPC, you just flip the switch on, save it, and then everything is back to Cloud EPC settings. Okay. Some other things to point out, we do have some kind of MOCN feature here, so you could add, secondary PLMN IDs. So if you have maybe you have some roaming agreement with that customer or some other operator, you could enter multiple PLMNs here. And then for each PLMN, you can define which MME IP they go to. And then lastly, the power levels here can be adjusted as well. And if you need to temporarily disable RF or for whatever reason, that's also done here. But most of the radio kind of changes are all done on this one page, and core changes if needed. So, but anyways, when the Cloud EPC is enabled, this page, and you save it, this page will be reprogrammed. So if you did make any changes here, this will be reconfigured. Okay. So on to LGW. So right now you can see we are in the bridge mode. So if I had this set to NAT, this part can be ignored because it's NATed. It doesn't really matter what this subnet is. It does matter when you're using router mode. When you're using router mode, you would set, you're basically setting the subnet, but instead of putting, like a 0/24 kind of thing, the way that it's entered here, you would enter the first assigned IP address. So if, for example, this was the subnet I want to use in router mode for all the LGW IPs here, you would set this to 255.0, and then you would set this to the first assigned IP address. And then for the one feature you do get, though, with router mode is you could set a range that you want to use for static assignments. So if there was a particular, say, IMSI, and you want to give it a particular IP address, make it statically set, you can do so in router mode. But again, the simplest might just be use bridge mode so that the IPs assigned are from your network, and yeah, this is just what's more commonly used. But yeah, if I was in NAT mode, the difference on this page would be that the IP address listed here would be the same IP as the HaloB. And it would have port, so this would be the port appended to the IP address. So when you were to click on the link, it would go to the IP and the port, which is the last, 5 and then the last 4 digits of the IMSI. And so in this example, the IP address listed here would be in LGW NAT mode. Is going to be, well, it's going to be the static IP right here, so 130.85. Okay. On the HaloB side, so again, default configuration is set for cloud OMC. If you have your own OMC, third party, whatever, this is where you would change. This is your ACS server URL. And then this is where you would enter the cloud key. And just to point out on the CPE, under tier 6.9, CPE also has the cloud key field here. There's also the nickname. This is like the name of the CPE, so we can show that a little bit later. Every HaloB and CPE can be set right from the OMC or within the device itself. It can be set a name, so it's more easy to recognize when you're looking from the OMC side. Okay, so here we have under sync settings, by default, it will be set to GPS sync as enabled. If you're trying to do some lab testing, it might be quicker to just disable it if you're not able to pull a signal, because if you leave it enabled, it's going to add maybe 2-3 minutes to the startup time, because it's going to try to sync. So if you didn't attach antenna or you just can't get signal, it'll keep trying to synchronize, and so in that case, it might be better to disable it just for the purposes of on-the-bench configuration. But of course, for the field, you want this enabled. There's a switch up here called force. Now this is depending on the HaloB as well for the NOVA 233 and the NOVA 227 in TDD. This is the, and 246 for TDD. So there's this option here, force sync switch. If we enable this, what this will do is if the GPS cannot sync or the GPS becomes out of sync for whatever reason, the HaloB cell status will go to inactive. So this will prevent the cell from interfering with neighbors. If you leave it disabled, it will not affect the cell's status. So if the HaloB cannot get synced by GPS or falls out of sync, the cell will still be active, but it's not aligned timing-wise anymore with the with the neighbor cells. So it could potentially cause interference. So it really depends on the situation. If it's a ultra rural, maybe there's not many base stations around it, maybe you can leave it disabled just to make sure the service is not impacted if the GPS stops working for whatever reason. But if you have a lot of cells in the area, you probably want to enable this to avoid interference if the GPS stops working. Another option could be 1588. So this is something that could be enabled as well if you didn't want to use GPS. Okay. This particular unit, it seems I don't have a HaloB license. Let's go to license management. Yeah, there is no license here, so I cannot enable it, but normally if you have the license, it's just a quick drop down to enable and save, and that's pretty much about it for the HaloB embedded EPC function. Okay, I won't go too much into neighbor setup, mobility parameters, other than I already went and touched on the cell selection, which, you know, could be important if you're, you know, wanting to allow a tighter or, you know, more conservative range. You know, this can be adjusted here. But, you know, for everything else, you don't really need to worry about it too much unless you truly are doing mobility. And then at that point, of course, you would adjust these different thresholds here. On the advanced page, you know, some of the things we could do is if you're doing X2 handovers, you could enable that instead. A lot of these parameters you really shouldn't or need to because they're pretty much already optimized. So most of these power parameter settings, you know, there's not much reason to change them. You can set the HaloB name here. This is something worth pointing out. So because the majority of our customers, at least in the US market, have been using it for fixed wireless, so what we did is the default setting for UE inactivity timer is very, very long. I think it's, so you can see right now it's set to 600,000 seconds, and it has to expire 100 times before the UE actually goes inactive. So I think it's like months before the UE can actually drop to inactive with no data. The reason it's set like that is because for fixed wireless, there's usually not a reason to make a UE go inactive. So it's you know, this is just set, you know, very to pretty much never happen. For mobility cases, you would probably change this, right, to much lower numbers. Okay. The other thing is maybe point out, so random access, if you have so I guess a couple things here. One is there's a lot of distance impacting parameters in LTE. You know, if we go to, let's first go to the quick settings. So under quick settings, this parameter here will for surely impact your coverage, your distance. If I remember right, I don't know if it's 14 or kilometers or less for special, or 16, something around there. So special subframe pattern 7, you know, will reduce the coverage just by that. If you need to increase the coverage, you can change this to 5. And this is basically your guard period. So 7 has a pretty small guard period, 5 has a very big guard period. So if you had to have extra coverage beyond the limitations of subframe 7, special subframe 7, you would just change this to 5. Okay, that's 1 point. And then if we look at the random access RC settings, okay, so here we also have preamble format. Preamble format 0, I believe, is also around 14 kilometer, 16 kilometer kind of range at most. If you need to increase that range, you could change this to 2, which you'll also see a pop-up that you cannot use a subframe 2 with a preamble format of 2. So we would have to change this to 1 on the other page. But you could change this to 2 to further increase, the coverage, which at that point I think goes to 28 kilometers for preamble 2. But if you're not trying to go too far distance, just leaving it at preamble 0 is okay. The other thing then is the zero correlation zone config. This is also distance impacting. So I think 10 will also limit it. It's better to find charts for what the actual distance is for each one. But I know like 10's around 5-6 miles at the most. So some customers would also need to adjust this, let's say, to up to 14 to allow for further coverage. So if you do need to go to greater distances, obviously there's path loss and physics in play as far as how far the coverage can actually go, right, depending on your power, your antenna gains, and so forth. But there's other settings within, LT and UNOB itself that, you would have to change if you need to increase the coverage. And so one's the special subframe assignment, one's the preamble format, and then the other is the zero correlation zone config. Okay, and another subject is, for PCI planning, that's just as important as your frequency planning, but there's another element for random access, also called the RSI, the root sequence index. That's this setting here. This also needs to be unique. So think of this kind of similar like your PCI. There's further details we could go into this, but anyways, if you have the same root sequence index on all of your UNOBs, it can also cause conflicts with your random access. So yeah, so this would be another setting to look at.
Hey, Jesse, going back to zero correlation, we did get a question in. It said, what is the trade-off for zero correlation equaling 14?
I'm trying to think what the throughput difference. The NCS, I think it's also like kind of guard period is set a little bit longer, but the biggest impact as far as it pertains to the throughput is going to be the special subframe pattern, because the guard period that gets changed here, here. So if we go to 7 to 5 here, your downlink will be impacted for sure, because if we look at a special, let me see if I open up another page here. Frame configuration chart. Let me see. Okay, so here is one such image that I'll try to bring up here. Okay. So when we're at 7, our guard period symbols is only 2. And if you look at what is the special subframe configuration made of, we have our downlink symbols. Then, so a big part of the special subframe is downlink, right? So you could almost treat special subframe like another downlink subframe. And so, you see most of this is still downlink. Then you have this guard period, and then you switch to your uplink. So we see we have, 10 downlink symbols, 2 guard period for 7, and then 2 uplink. When we switch to 5, now we have 9 guard period symbols. So the guard period, the timing is much longer. And now we only have 3 downlink symbols. So your downlink definitely takes a hit by going from 7 to 5. On the zero correlation zone config, that's more about random access. It's not, I don't think that's, you know, too much impacting on the throughput, you know. But the biggest impact is going to be on you know, it's going to be here.
Okay, we did get another question there. Is there a parameter guideline showing the range and trade-off for all parameters?
I don't know that there is like a very specific, right, guide that goes into that level of detail. Like if you look at our user guide, it kind of, you know, gives a quick maybe description for the parameters, but I don't think there's like a specific like cell radius setup guide that, you know, points out every parameter, what the trade-offs are and such. We do have some like buy tips on our community forum. And so I know like it's kind of lightly touched here. Like here's one, this is like back a while back, but yeah, I'm trying to think how much of this, like we occasionally have these buy tips that talk about it, but it's not at the, maybe the length and detail as far as, you know, what all the settings are. And yeah, so.
Okay, I did post that link in the chat if anybody wants to go look at that page themselves.
Okay, so moving on a bit, so again, working mode would be setting what your maximum users allowed is. By default, this is 32 for the 227, 233, but you can change it to 96. There is a trade-off here, though, because the number of users per TTI isn't increasing, so the latency will go up when you change this to 96, and that's just because the queue becomes that much longer. So now you have, you know, up to 96 users being scheduled, and, you know, so there's going to be a latency increase. So that's why the default's 32, but if absolutely needed, you can increase this. But this would be the number, the maximum number of active and connected users. Okay, following that, as discussed, PFS is one of the newer schedulers we added. The default is RR, but there is a kind of a weight here, like a scale we can do between 0 to 100. So if I put this at 0, basically PFS is just like RR. There's pretty much no difference between PFS 0 and RR. PFS of 100 means, you know, that PFS is solely, logic is solely used for all scheduling, but the problem is when you do that, the edge users, you know, will have probably high latency because they're not going to be scheduled as often. You know, so there's like a balance of 50 set by default, but this number could be played around with to, you know, see what works best for certain environments. But again, PFS will consider the UE's QCI and, you know, what is the average throughput, you know, over a period of time when deciding on, you know, what priority level to give it. Okay, and then we have this link activation state detector. This is enabled by default, and this is just the watchdog. Just think of it as a watchdog for the S1. So if your HaloB disconnects from the MME, and so this is enabled by default set to 10. So after 10 minutes of the HaloB being inactive, it will reboot on its own. So this is to recover maybe there is some software issue. You know, this is just kind of a watchdog to help bring the UNOB back to service if something was to happen. Okay, this is, as I mentioned, this is kind of a newer feature, but we do have ICIC, but it's just hasn't been that frequently implemented here. But you can decide, you can set like which PRBs you would like to use, right? So you can kind of statically set that range if you're trying to do reuse one, say on 3 sectors. I did see a question come in. Max, did you want to check that?
Yep, you're right. On the scheduling algorithm, isn't the max CI algorithm supported anymore?
Technically, we do have it. It's not an option here. The reason that it's not selectable is because max CI has not been fully tested yet, but it is a feature. Like, we could probably enable it in the back end, but because it hasn't fully went through all of our testing, and it hasn't been that requested yet, so it just hasn't made its way to be a commercial feature yet. But yeah, for those that don't know, max CI doesn't, you know, it's pretty similar to PFS. It's just not factoring in throughput. It only cares about the CQI of the user. So PFS is quite similar to that anyways, but yeah, at the moment it's not I wouldn't call it a GA feature just because it's not fully tested. There's another question?
No, that was just them thanking you for the response.
Oh, yeah. Yeah, I mean, there's probably a lot of details going. I know we're trying to cram it into a short period. For certain base stations, they have the signal trace feature. What this allows, and we do have a user guide on this, but what you can do, so one, if you enable this, you could enter the IP address of your computer, and it will be fed into Wireshark. So if you're running Wireshark on your PC, you enter this IP address, and there's a user guide that explains how to filter for the packets. So if you're trying to read individual RRC and SCTP messages, that can be done, you know, by pointing them to your computer's IP, and then opening Wireshark, and there's a couple settings, you know, you would need to configure, but and then run the filtering, and you know, so anyways, there is a way for troubleshooting by using Wireshark using this method. Yeah.
See, the user guide can be found on the website under the documents section. So if you go support documents, you should be able to find the user guide there. If you still have trouble finding it there, you can send an email to support_NA@Baicells.com and they'll be able to get it to you directly. I will look for the link to put that in chat as well.
Okay. This one's worth pointing out too, multi-element. So if you are using multiple VLANs, you could set different VLANs for, you know, to bind to S1U, you know, for example, or tier 6.9. So you know, so binding can be done here. And some of them might have, in this particular model, we do have a 64 QAM. This was upgraded from an old release. I know all new releases have this enabled by default, but you know, if you want 64 QAM, this is for uplink. So 64 QAM uplink, both of these need to be enabled, but it should really be enabled by default. But I think this unit was on an old release, got upgraded, and these did not change. So, but yeah, normally this is enabled. Other than that, I think I covered the basics. on the HaloB side here. I don't know of the audience here how much are based in US that would be interested in CBRS, but that's probably another full topic that would take more time.
Yeah. We don't have enough time to go over the CBRS topics. We do have some videos on our YouTube channel that do go over the CBRS topics. However, I think most of our audience here isn't in the US. Okay.
And do we have any more time to maybe do a quick skim through the Cloud Core OMC and BOSS?
Technically, we're out of time. We'll leave that up to you, though, as you're the presenter here.
I'm good. I mean, I could probably, it's pretty basic. I could probably get through it in 5–10 minutes if everyone else is okay with that.
Yeah, sure. And just for reference for everybody who is here, we are recording this session. We'll be sending out a link to the recording after we're finished. So if you need to leave and you still want to watch these last 10 minutes, you will get a link for it later. But yep, feel free, Jesse.
Okay. So again, I'm on cloudcore.baicells.com. I know there's another URL. They all go to the same address here. So here I'm going to log in with my test account. And this is going to be the first kind of page that comes up, kind of summarizes the alarms, you know, which, number of HaloBs active, inactive, and so forth. But really the most important pages here are the HaloB and CPE monitor page. So I have a lot of test devices here. So let me pull, what I'm going to do here is I'm going to grab the serial number and just search for that guy. Okay, so here I can see the little green indication here shows it's online. I can see there's a UE count. I can click on the UE count, which should bring me the list of the IMSIs, and there are different measurements here. So just like the UE info page on the base station. And if we scroll over, we can, see all the common settings here. And again, this is adjustable. So if I wanted to see, some of these in a separate order, right? Like active status is probably, more important. So let's move that up. And MME status is also quite important. So let's put that there. And so it's customizable. There's an export button if you want to read it in Excel instead. But yeah, we can just scroll over and see some of the settings here. If we go to the information of this particular HaloB, we can see again the alarms. What are the historic alarms here? And performance section will help show different certain KPI stats for this guy, right? It's just a lab unit, there's not much going on, so not that pretty at the moment. And we kind of already went through the slides discussing the upgrades and, all the other stuff you would kind of expect. If, let's go to inventory device, so I think they might have renamed this in the last upgrade, so it might look a little different, but it looks like now it's under inventory and device. So again, if you didn't enter the cloud key in the device itself, you could go ahead and add it manually in here if you know what the serial number is. And you can also create device groups, which you can use when you're setting up permissions. So if you only want certain users to access certain base stations, you could group them into their separate groups, right? So I can select a number of HaloBs here and move them to whichever group I want. Okay. On CPE monitor page, let's look at one of these IMSIs. Let's say this one here. I don't know, just pick one. Okay, now I see 2 here, so this IMSI must have been in another CPU that's now offline. But here we can see the different stats here as well. And if we click on the history button, we can see, you know, over time, you know, what are the different stats we're seeing. So. Okay, and we can see that there's an unlock symbol, and so it looks like before, whatever CPU that was on it, that SIM card was in before, it did have a PCI lock, because that's what that symbol looks like. But we can go to settings, and we can also lock it here. So that icon indicates that it is locked to a particular cell. We can see that remote access to the HTTPS is enabled. And if we want to give it a name, maybe the name of the customer, we can do that here as well. Yeah, so I'll try to see what else to run through. BOSS is the other important setting here, or the section. So this is where you manage your SIM cards. So firstly, if you get a pack of SIMs, you would import them here, so network SIM card, and then I'll say import. And if you buy SIMs from us, they will have activation codes on them. So you could enter the activation code, which will import all of them, you know, related to that code. There's a file method, so you could export the template, just input all of your IMSIs, and then import that back. So those are the 2 ways to get SIM cards into your account. You would also set up some service plans. So depending on what your downlink and uplink, you know, plans are, the HaloB will do the rate limiting for you. So you don't need to do any particular queuing or traffic shaping elsewhere on the network. Actually, the traffic shaping is done from the HaloB itself. So, and it will rate limit based on the settings here. And so then on the subscriber page, we can see the status of each subscriber. If we wanted to add a new subscriber, adding a subscriber is activating the SIM card. So we would enter their information. We would then associate it to one of the available IMSIs on your account, and then you would associate it to a service plan, and then save, and hit OK here. And at that point, that SIM card is active and ready for use. And then lastly, if you click the Cloud Core, the very top left, so this is only going to be there if you're using Cloud Core, but this is where you could change your kind of company information. This is where you can add more users to your account, and then this is where we can go to invoice, billing. So yeah, and as I mentioned before, we're charging $1 per active IMSI. So it will calculate, you know, throughout the course of the month, it's post-pay. So it will look at the previous month to see which IMSIs became active and, you know, how many days they were active. And then based on that, it's going to do $1 flat per IMSI, and can see all your billing and pay online, set up auto pay, that sort of thing. So that's all done here. But this is only for the Cloud Core. If you have local OMC, you won't see that. It'll just be the OMC side, or local BOSS, yeah. Well, I think that's a quick skim through the OMC side and BOSS side. It is, you know, fairly straightforward. Once you get added a few devices, I think it should, you know, come pretty natural as far as the workflow, what you can do. But, you know, most settings, you know, you can configure things from the OMC, you know, but you can also configure them from the device itself. It just really depends how you want to do that. yeah, so I think that helps do a quick summary of it. So yeah, any more questions? Yeah, we'll open it to that.
Sure thing. I do want to say just thank you, Jesse. Thank you, Yen, for taking your time to take us through this training here today. As we wait here to see if there's any last remaining questions, just one final thing. As I already mentioned, we have been recording this session. We will be sending out a video to this, so you can share that with your teams. However, it is going to take a day or two for us to complete the video to send out, so it may appear early next week before we are able to send that out. All right, we're getting some thank yous for you, Jesse, but I'm not seeing any more questions, so I think we'll wrap it up here.
Okay.
Excellent. Well, thank you everybody for joining us here today. If you have any further questions, if you have issues with your products and you need support help, please contact support_NA@Baicells.com. They'll be able to help you with any questions that you may have. Also, feel free to take a look at our community forum, look through some of the posts that are in there. There's a lot of great stuff in the buy tips, and there might be a solution to whatever question that you may have there. So thank you very much, everybody, for joining. I hope you have a good rest of your day and a good rest of your week. Thanks. Bye.
Thank you.